Quasi-hereditary algebras, lecture 15, problem session. As a matter of fact, today we will solve only one problem. So here is the problem. Construct all indecomposable tilting modules and determine the Ringel dual for the algebra A given by the following quiver and relations. We have three vertices 1, 2 and 3, an arrow alpha from 1 to 2, an arrow beta from 2 to 3, an arrow gamma from 2 to 1, and an arrow delta from 3 to 2. And we also have two relations. Alpha after gamma is 0 and beta after delta is 0. So let's try to solve this problem. And we start our solution by constructing the indecomposable projective A modules. The projective module P3 is the smallest one. We start from 3, we can go by delta to 2, we cannot proceed by beta because of the relation. From 2 we can go by gamma to 1, and then we stop because of the relation that alpha after gamma is 0. So P3 has length 3. Now P2. Starting from 2, we can go by gamma to 1, and then we stop because of the relation, or we can go by beta to 3. And then from 3 we can do exactly the same what we did by construction of P3. And finally, the module P1, starting from 1, we can go by alpha to 2, and then starting from 2 we can do exactly what we did in the module P2. So here are our three projective modules. And now we can easily see that for the usual order, when 1 is smaller than 2 and 2 is smaller than 3, the standard modules will be as follows. So P3 is delta 3. If we factor out P3 from P2, we get delta 2, 2 on top and 1 in the circle. And when we factor out P2 out of P1, we get that delta 1 is equal to 1. So we have three standard modules, and clearly they have trivial endomorphism algebras, because Li in each delta I appears only once. And we can now readily see the standard filtrations of projective modules. So P3 is projective. P2 contains a copy of P3. If we factor out this copy, we will get delta 2. And P1 contains a copy of P2, which already has a delta filtration, and the quotient of P1 by P2 is delta 1. So we immediately see that our algebra A is quasi-hereditary. In order to be able to determine the tilting modules, we also need to construct the costandard modules, because tilting modules are those which have both standard and costandard filtration. So then let us construct the indecomposable injective modules. So now I3, we start from the circle 3, we can arrive to 3 using beta, and then we can arrive to 2 using alpha. And our relations prohibit anything else. So that's our I3. Our I2, we start from the circle which is 2. We can arrive to 2 using alpha from 1 or using delta from 3. And then to this 3 we can arrive as in the construction of I3. And finally, the indecomposable injective module I1, we start from 1 in the circle. To this one we can arrive from 2 using gamma, and from this 2 we can unwind the indecomposable injective module I2. And that's it. And using these pictures we see that we have the following costandard modules for our algebra. So nabla 3 is just I3. If we take away the copy of I3 from I2, we get that nabla 2 has circle 2 and top 1. And nabla 1 is just 1. It's a simple module, as expected. Okay, and we of course can see the costandard filtrations of the injective modules. The module I3 is costandard. The module I2 has a copy of I3 on the top and nabla 2 in here below this nabla 3. And I1 has a submodule nabla1 and quotient by it is I2, which has a nabla filtration. So we have a second verification that this algebra is a quasi-hereditary algebra. Note that the algebra A has a simple preserving duality, which corresponds to the anti-involution that swaps alpha with gamma and also swaps beta with delta. So in particular, the injective modules are just the duals of the corresponding projective modules, and also the costandard modules are just the duals of the corresponding standard modules. Great! Now we can try to start constructing indecomposable tilting modules. The first module T1 is very easy. T1 is just a simple module L1 because this module is both delta and nabla. It obviously has both a standard and a costandard filtration because it is both a standard and a costandard module at the same time. Next, we can note that if we take P1, there is a copy of P3 inside P1, and if we factor out P3 out of P1, we get a module of length 3 with top and socle 1 and 2 in the middle. So we get this module, and in this module we can easily see that it has both a standard and a costandard filtration. It has a standard module delta 2 as a submodule with a quotient delta 1, and it has a costandard module nabla 1 as a submodule with the quotient nabla 2. This implies that this module is exactly our T2. So the module T2 is isomorphic to P1 modulo P3. It remains to construct T3. So in order to construct T3, we use the construction of tilting modules as in the theorem about the existence of tilting modules. We start with delta 3 and try to universally extend it by delta 2 by putting delta 2 on top of delta 3. So how many delta 2's do we need? That's the dimension of the x1 from delta 2 to delta 3. In order to compute that, we know that the module delta 2 has the following projective resolution. So we have the module P2 and a copy of P3 inside P2. So let's go back. So we have P2, that's delta 2, and that's a quotient of P2 by delta 3. Okay, so the projective resolution of delta 2 looks as follows. So we have P2 and inside it a submodule P3. Now we need to take home from this resolution to delta 3. Delta 3 is P3, so the identity map on P3 is the unique up to scalar endomorphism of P3, and it obviously doesn't factor through P2 because P3 is an indecomposable module and P2 is another indecomposable module. So this means that the dimension of x1 between delta 2 and delta 3 is 1, which means that in order to extend delta 3 universally by delta 2, we should put one copy of delta 2 on top of delta 3. But we also know that P2 actually is a non-split extension where delta 3 is a submodule and delta 2 is a quotient. This means that P2 is our universal extension. So we did the first step. In the next step, we should extend P2 universally by putting some delta 1's on top of this module. So we need to determine the dimension of x1 from delta 1 to P2. Now the module delta 1 has the projective resolution, which looks as follows. We have P1 and inside a canonical copy of P2, and the quotient is exactly delta 1. Let's go back to our projectives. We have P1 inside a copy of P2 and the quotient is delta 1. That's our projective resolution of delta 1. Now we need to take a home into P2. The dimension of the home from P2 to P2 is 2, and also the dimension of the home from P1 to P2 is 2. But now let us note that the socle of P2 is just a direct sum of two copies of L1. Indeed, here we see that the socle of P2 is a direct sum of two copies of L1. But this means that the image of any homomorphism from P1 to P2 is contained in the socle of P2 and thus doesn't have any L2 subquotients, which means that no non-zero map from P2 to P2 factors through P1. And this implies that the dimension of x1 from delta 1 to p2 is 2. And so we can conclude that the module T3 is a non-split extension of P2 with 2 copies of L1 on top of it. We also have a non-split short exact sequence where P1 is in the middle, it has L1 as a quotient and P2 as a submodule. So it follows that T3 will be a non-split extension of P1 by putting one more copy of L1 on top of it. So now let us look at our module P1. So this is our module, 1 on top, and then P2 under this one. P2 consists of delta 2 and delta 3. And we see that we can put L1 on top of this 2. So we will get the following module. This is our copy of P1. This is our quotient L1. And the arrow alpha sends this 1 to this 2. This is a new indecomposable module. And we also can immediately see that this new module has both a standard and a co-standard filtration. So this is a standard filtration. So we have P1 as a submodule. It has a standard filtration and the quotient is 1. But here is a co-standard filtration. It has 1 and 1, so these are co-standard submodules. If you factor them out, here we have nabla 2, and if you factor it out, here we have nabla 3. So this module is indeed a tilting module, so this must be our T3. So here are our T1, T2, and T3 drawn together. T1 is simple, T2 has 1 on top, 1 in the circle, and 2 in the middle, and T3 is this complicated module. It has T2 on top, T2 in the bottom, and 3 here in the middle. Okay. We can now record the dimension of the home spaces between the individual Ti's and Tj's. So we see that there is one home from T1 to T1, and there is one home from T1 to T2, and there are 2 homes from T1 to T3. We can hit this or this so-called components. So the first row is 1, 1, 2, and since we have a simple preserving duality, the first column will also be 1, 1, 2. Next, the endomorphisms of T2. We have the identity morphism and also the nilpotent map, which sends top to socle. So the endomorphism of T2 is 2-dimensional. Now about morphisms from T2 to T3. We are not allowed to hit this 3, so we can either hit this copy of T2, this gives us 2 morphisms, or we can hit this 1. This gives us 1 more morphism. So this dimension is 3, and similarly, homes from T3 to T2, this space is 3-dimensional. And finally, the endomorphism space of T3 has dimension 6. Indeed, we have the identity map, then we have 4 different maps which send 2 top components of this module to 2 socle components of this module, and we have the map which sends this copy of T2 into this copy of T2. 1 plus 4 plus 1 means 6. Now let us construct some special homomorphisms between tilting modules. We have a surjection from T3 onto T2 with the kernel, which is generated by 3 and this 1. If we kill this part of T3, we can surjectively map this onto T2. We denote this by Xi. Then we have the injection of T2 into T3. We can embed this copy of T2 into this part of T3. We call this eta. So we have a surjection from T3 onto T1, which we call pi, which takes this top component of T3 and maps it onto T1, and the rest is in the kernel. And we have an injection from T1 into T3, which we call iota, which takes T1 and embeds it into this socle component of T3. Now we can make the following observations. Psi after eta is 0. So if we take the module T2, embed it here, and then project onto this copy of T2, the composition is 0. Also pi after iota is 0. If we take 1, embed it here, and then project it onto this copy of 1, this should be 1, then of course the composition is 0. And finally, we observe that the composition of pi after eta, after psi, after iota is also 0. So if we take this copy of 1, embed it here, and now we project it onto this copy of T2, and now we embed this copy of T2 into our module T3, and then project onto the top component, the original 1 goes to 0. So we have 3 natural relations. And this implies that the Ringel dual of A is a quotient of the algebra which is given by the following quiver and the following relations. So we have 3 vertices, 1, 3, and 2. The arrow iota from 1 to 3, the arrow pi from 3 to 1, the arrow psi from 3 to 2, the arrow eta from 2 to 3, and the relations that pi after iota is 0, psi after eta is 0, and pi after eta after psi after iota is 0. So let us now determine the indecomposable projectives for this algebra. We start from P1. If we start from 1, we can go by iota to 3, and then we cannot continue by pi because of the relation, so we go by psi to 2, and then by eta to 3, and then we cannot continue anywhere because of the 2 other relations. So this is our P1. Next, let us take P2. We start from 2, which is here. We go by eta to 3. We cannot go by psi because of the relation, so we proceed by pi to 1, and then we can do all the things which we did for P1. And finally, for P3, we start from 3. We can do psi to go to 2, or pi to go to 1. If we arrive at 2, we can do everything what we did in P2. If we arrive at 1, we can do everything what we did in P1. Great! And now we can check the multiplicities of simples in these projectives. So P1 has L1 with multiplicity 1, L2 with multiplicity 1, and L3 with multiplicity 2. And if we check this table, we see 1, 1, 2. P2 has 1 with multiplicity 1, 2 with multiplicity 2, and 3 with multiplicity 3. And we look at this table, we see 1, 2, 3. And finally, P3 has 1 with multiplicity 2, 2 with multiplicity 3, and 3 with multiplicity 6. So if we look at this table, we see 2, 3, 6. This means exactly that the multiplicities of simples in projectives match our recorded multiplicities of dimensions of home spaces, so the Cartan matrix of our algebra, and this means that our Ringel dual coincides with the algebra given by this quiver and these relations. We can also see from our pictures of projective modules, and we have the following standard modules for this algebra with respect to the opposite to the natural order. So delta 1 is just P1. So P2 has delta 2 on top if we kill the delta 1, and delta 2 is 2 on top of 3. And P3 has here a copy of P2 which we kill, and here a copy of P1 which we kill, so delta 3 is just L3. And all these modules clearly have trivial endomorphism algebras, and also the projective modules clearly have delta filtrations. So this is a delta. P2 has delta 1 here in the bottom and delta 2 on top, and P3 has 2 delta 1s, and then delta 2, and then delta 3. Consequently, we also see that our Ringel dual is a quasi-hereditary algebra. And we also see that it has a simple preserving duality, which is given by swapping pi with iota and also swapping eta with psi. This completes our problem. Some extra problems and questions. Problem question 1. In the above problem, check that the second Ringel dual of A is isomorphic to A. Problem question 2. Compute first extensions between all standard A modules. Problem question 3. Compute first extensions between all standard R of A modules. Problem question 4. Compute first extensions between all costandard A modules. And problem question 5, compute first extensions between all costandard R of A modules. Thank you very much and see you next time.